homework. So let's take a look at the first page, 2 pages, 3.1, the mixture problems. Was there anything there that we need to take a look at that was particularly fun or grueling? No? Come on, there must be something we can do. Wasn't there one where the amount of liquid pumped out of the tank was different from the amount going into the tank? I like that one. Which one was that? Is it 25? Yes, faster rate. Yeah, let's take a look at this, just so that we can have a review real quick, since no one wants to ask and I've got a quiz. So I've got my tank. So I guess we have to back up and take a look at 23. So 23, it says that it's filled to capacity with 500 gallons of liquid. And it says that brine containing 2 pounds of salt per gallon. Okay, so it says pure water starting out. So the salt in the tank at time 0 is 0. And then it says that brine containing 2 pounds per gallon. Let's see. So you have 2 pounds per gallon of salt. So 2 pounds per gallon is being pumped in at 5 gallons per minute. So see how I got it in the pipe there? So that I can just easily compute the amount, the salt coming into the tank, just multiply those together. And then coming out of the tank, you have 5 gallons per minute. Okay, so you have salt in, so ds over dt is going to be the salt in, which is 10, constant rate, everything's good. And then the salt out will be the rate times the concentration. And the concentration is the thing that is varying. So let's see, I'll just rewrite this. ds over dt is 10 minus, so the rate is 5. The concentration is S over 500. Because there's S, whatever, how much salt there is. So if there's a pound of salt in that tank, then the concentration would be 1 out of 500. So whatever the concentration is. So there's your differential equation. Let's see, ds over dt is 10 minus 1 over 100s. So this is a pretty easy differential equation to solve. Might as well do it since I've got it here. So I have ds times 1 over 10 minus 1 over 100s. I feel like this could be easier. You know what? I don't like the 100 there. Let's get rid of it. Here's what I could do is I could just call this S and make this 1000. And then on the other side, I have 1 over 100. Does that work out? Because if I multiply both sides by this, I'll get 10 minus, yeah, that works out. So that way I don't have to deal with the fraction on the left side. Okay, now I can integrate. You might have done this a little differently. It'll work out the same. Natural log of this, put a negative out front just for good measure. And then we get 1000 minus S is equal to C1 e to the negative 1 over 100t. So I think that's what we end up with. So S is equal to 1000 minus e to the negative 1 over 100, 1 over 100t. Does that look good? C1. And to get C1, you have to realize that S of 0 is equal to 0, because we start off with fresh water, and that means that C1 must be 1000. So S is 1000 minus 1000 e to the negative 1 over 100. Does that look right? Right answer? All right, that wasn't too hard. Okay, so it gets way harder though when you introduce this variable. So I love this. This is so much fun. So, which I know that makes it so much hard. So let me just copy this. So same picture. Copy. We'll go down here. and we'll see how this changes things. So now this is number 25. And the big difference is that instead of 5 gallons per minute going out of this, you have 10 gallons per minute. So that means that the volume of the tank at any given moment can be computed as 500 gallons minus 5 times T, where T is measured in minutes. So that's how much liquid, the tank is slowly being drained, 5 gallons per minute, because you have 5 gallons going in, 10 gallons going out. Do I have this right? The rate, yes, pumped out. So here's the difference is you have ds over dt. Salt in doesn't change. So you have the 10. It's the salt out that changes. So you have 10 times the concentration. The concentration is not S over 500 because the volume is no longer going to be 500. The volume is this. So it's S over 500 minus 5 times T. I regret having an S there because it looks too much like a 5. But you can see that this is no longer separable. So sadly, it's not separable. So it is linear though. So you could use the linear differential equation techniques. And does it actually have you do that? When is the tank empty? I guess so. So you'd have to solve that thing using here. If you really want me to, I can do it here just a minute. So ds over dt plus 10 over 500 minus 5t times s is equal to 10. Oy, oy, oy. I have my my integrating factor. I was going to use Python, but now I'm getting too lazy to do that. So presumably you could do this. You get some sort of weird expression. I don't even know. Okay, I'll do it. Just a minute. Sorry. I know I shouldn't be so lazy. Here, let me grab some Python. I don't want that Python. Just a sec. Let's see if I go to, let's see, GoLab. There it is. Let's see, what do I have here? Calculus. Let's do some calculus. Okay, just a sec. Let's see, we'll do this. And then we'll move down one. And then we'll integrate. So this is what we need to do. Integrate, what is it? 10 over 500 minus 5 times t. Shut up. Let's see. Whoops. Come on. Did it work? Let's see if it worked. Yes, it did. Okay, so it's the -2 times. Oh, okay. Well, that's not bad. So that means that the integrating factor, where's this? That's not too bad. So the integrating factor is, sorry. You think I could remember? Okay, log t minus 100 to the -2 power. Okay, so this is going to be e to the ln of t minus 100 to the -2. Did I get that right? T minus 100? Yeah. Okay, I'm going to just trust that Python did it right. So that means that this is going to be 1 over t minus 100 squared, interestingly. Is that at all related? Oh, it is. It is related to this because that's 100 minus t. Well, 5 times 100 minus t. Well, anyway, so presumably you could multiply through, do some work that I'm not willing to do at this moment and get the answer. But at least we got another step closer. But this is a linear differential equation. So that's the first page. I just don't want to take the time because we have other things to do. Unless you're dying to know, which you can do later if you need to. All right, so let's see. Second page was mixture problems that were multiple tanks. And this one, you didn't have to solve them. Wait, you didn't have to do number 10, did you, or did you? Did you do 10? Oh, you did do 10. Whoops. Let me see. Did you have to solve that? Oh, they wanted, oh, without solving the system. Oh, okay, good. Oh, yeah, that's easy. Yeah, without solving the system. Okay, well, we'll talk about that in a minute. But setting up your system, were you okay setting up like multiple differential equations? Yeah, what do you think, Luke? Yeah, let's take a look at 9b. Um, okay, so let's see. So let's see. Oh, interesting. Okay, let's see if we can do this. So first off, dx1 over dt. So I'm not going to bother redrawing this, but dx1 over dt is going to equal, let's see, we're moving 2 gallons per minute out of, does it say how much? It starts at, let's see, x1 of 0 is equal to 100, and x2 at 0 is equal to 50. So anyway, we've got this. We have the mixture. Wait, why is it moving slowly? They're different rates. Sorry, let me see. Do we start off? Each are partially filled with 100 gallons of brine. I don't like this one anymore. I thought those were constant rates when I looked at it when I assigned this. Okay, well, I've assigned it, so I've got to do it, don't I? Okay, so the dA over dt is going to be 2 gallons per minute times x1 over 100 plus t. And the reason for that is that you have the concentration or the volume of tank A is going to increase by 1 gallon every minute because it's getting an extra gallon every minute. And then you're going to subtract, or wait, that's minus, aren't we? That's 2 gallons flowing out of the tank. And then into the tank, there are 3 gallons, x2, however much salt is in tank B, divided by 100 minus t. Interesting. And then dx2 over dt is equal to pretty much the opposite. We have, let's see, 2x1 over 100 plus t minus 3x2, 100 minus t. Huh. Okay, so that's that. That was the easy part. Find a relationship between the variables that holds at time t and explain why this relationship makes intuitive sense. I guess when I looked at this, I thought those were constant. I mean, it was constant volumes. And I haven't thought about this enough to be able to help you out with an answer. So my apologies. If they were constants, we could figure this out pretty easily. But yeah, the variables, it's the denominators here that are bothering me. So I apologize. I'll have to pause and try to get this back to you on Monday. So this is my homework now. Homework. But setting this up was pretty straightforward, right? I mean, well, actually, yeah. The variable volume, I didn't catch that when I was looking these over. So that's no good. So we'll save that one. This is for me homework. I'll do my best to figure this out. It's going to bother me. Probably it's something relatively easy, especially since it says explain why this relationship makes intuitive sense, but trying to figure out something intuitive since I am an ISTJ. Wait, is that intuitive? Yeah, I guess I should be able to do it, but not happening. Okay, so, oh no, intuitive is in, right? I'm sensing. In, in. Yeah, the I is for introverted. Yeah. So yeah, so I'll blame it on my lack of intuitive sense that I'm an ISTJ, not an INTJ. Okay, so I'll come back to that. I'll try my best. Are there other things Or should we do our, let me see, how bad is this? Is this going to take forever? Just a minute. Write a differential equation. It's only one tank. Look, I've got a nice picture. Write a differential equation, solve. It should be separable. It is. And how many pounds of salt will be in the tank? Yeah. Yeah, this shouldn't be too bad. Do we have time though? 2:30? Why don't we try it out? We'll see how far we get. This will be fun. Give me something to put in the grade book. I think is that 2? Yeah. You just need 1. Here's some more. There's probably too many. Here you go. Here, I'll just give you a big stack. Make sure Cooper in the back. So Cooper, give 1 to Cooper. Do you have extras? Really? So many. Make sure. You got at least 2. Good. All right. I'll put it up on the screen for the people watching from home. And then we'll see if we can get her done. There. Isn't that nice? Yeah, so if you want to see it in full color, you can see it up on the screen. Freeze. 100. Oh, duh. Mm-mm. All right, hopefully you're coming down the home stretch with this. I know it's fun to work on, but probably need to move on here in a bit. So when you are done, once you're semi-satisfied, nice. Usually you'd like to ponder more. Box it up. I love it. See if I need to take it off your hands. Nope, not yet. Curious. Oh, you guys are done. Wow. All right, I'll take what you got. Nice. You got a box around it. You want me to simplify it for you? That's fine. That's fine. I can simplify it. That's fine. That's fine. All right. Nice. There we go. I don't want anyone to be bored, so here I could put this up on the screen. Just a sec. Not that. Oh, why is it like that? Just a sec. Still weird. Oh, it's frozen. That's better. There. Yeah, that should do it. Yeah, so this will be the first thing that we do. If you get bored, you can try to figure out what C1, C2, and C3 are based on those initial conditions. So I'll tell you the first step is to do the derivatives. So I need the first, second, and third derivative of, wait a minute, C1, C2. Hold on a sec. Oh yeah, C1, C2, C3. Okay. Yeah, so first, second, and third derivative of that function. Here, let me get rid of this. That's confusing. There. So first, second, and third derivative. So if you get bored while you're waiting, we need to do the derivatives. I think we only need the second derivative. So first and second derivative should be okay. You're all set? Answer on back. All right. Very nice. I like it. Very nice. Works. Still thinking, oh, you know, some people didn't want to simplify. And so if you don't want to simplify or put it into your calculator, you punch it into your calculator. If you have a decimal, then you did punch it into your calculator. That's fine. But you don't have to. You could be, if you don't want to pull your calculator out, you can just box that, hope for the best. Hope for the best. Okay, good, good. Box it up. Let's see. Yeah, same with you? You're just going to, you box it up, I see. Yeah. Wait. Okay. I can as well. Very nice. But I appreciate your self-awareness, you know? Well, you know that it's not going to be like, what is that? I mean, sorry, is that? That's like 10 to the 1000th. That's like a huge number. Okay. Is this good? Is this mine? Yes. Okay, we'll take it. Yeah. No, that's a good one. Look, this is, oh, yeah, 10 to the 15th. Probably not right. I know. I got a couple more. Is yours 10 to the 15th? Is it a decimal? Oh, no, that's in the ballpark. All right, do I have all the quizzes? Okay, yeah, let's go put you out the misery. Let's see. Well, I haven't been looking at the top. I was most interested in how you answered the first part, not so much this. So this part, you know, this. Well, I guess that letter number 1. writing the differential equation, because if you can't figure out how to write the differential equation, then all is lost. So let's just remind you how you do this. You have the change in salt with respect to time. So ds over dt is going to equal salt in. How much is going in? It's going to be 6 pounds per minute minus the salt out. So that's going to be the concentration times 3 gallons per minute. And so this, you should have something like this. So 3s over 500, and s of 0 is equal to 20, was it? Yeah, 20. So this is the answer to number 1. Yeah, and if you don't have this differential equation, then of course, yeah, the rest of it is no good. Right. Oh, okay. So if you know what you did wrong, then you're in good shape. I mean, that's what the quiz is for. It's so that next Friday you do it right, because you'll have the same problem on the test next Friday with this look how beautiful my pipes are. I just want to point out, I took a long time to make the diagrams look good. But anyway, I probably could make my tank. My tank doesn't look that great. I need to put more of a fade, don't I? Okay, but anyway, so there's what I've got. I've got the same thing over here, but I didn't show my work as much. And so then I'm solving, and the fractions, I can't stand fractions. And so the fewer fractions I have, the better. And so what I do whenever I have a problem like this is I factor out the fraction. So I factor that out of my expression. And you might say, how did you do that? Well, this part is easy. 3/500ths times s is this, right? The other one is a little harder, but you can do this on your calculator pretty easily. You do 6 divided by this, and you get 1,000. And so, so anyway, there's my factoring. So that makes it a lot easier to work with. Now that I've got that, it's a separable differential equation. I've got this down at the bottom. I did my integrals of both sides. Here's why this is so much better to not have a fraction here, is because when I do this antiderivative, you know what it's going to be. It's going to be the natural log of this. So anyway, let's just put that down with a negative. And then I kind of skipped a few steps and got down to this, but I think you know which steps I skipped. So S was 1,000 minus C1 or whatever times e to the negative 3t over 500. And then I plugged in my 20 to get my initial value, or the constant, and the constant was 980. So here's my my stuff, and then there's my my S of 30 once I plug 30 in. So anyway, I'm not sure. Like hopefully, like I said, hopefully you got this one right or something up there, and then this is a little bit harder, and then if it's not, like this is why I said that if you got like 50. You're in better shape than the person who got 10 to the 150th or whatever. So those giant numbers. So anyway, let's move on. So I said that we're going to be doing this, so let's go do it. Well, I guess what I'm trying to point out here is that a general solution for a differential equation that is more than just a first order. So this is a third order. Whoops. Come on. There it is. Third order because of the third derivative. So we have a third order differential equation. This is what the general solution would look like for that differential equation. And what I want to do is I want to use this to come up with some, use some initial conditions to figure out what the constants are. And so to do that, I'm going to have to find the derivatives. So we have c1 e to the x plus c2 e to the 2x. 2c2, plus 3c3 e to the 3x minus 1/2. I guess get rid of that. So minus 1/2. And then the second derivative is just c1 e to the x plus 4c2 e to the 2x plus 9c3 e to the 3x. So here I have three derivatives. Well, the function in two derivatives. So I have three functions. And so if I knew what y of 0 was, and y prime of 0, and y double prime of 0, what that would give me is it would give me three equations and three unknowns. And so presumably I could use that information to come up with the values of C1, C2, and C3 using a little bit of linear algebra or maybe a little bit of just basic algebra if I'm clever about it. I realize now that I don't want to do that at this point in the game. However, I do want to point out that whenever you have a differential equation that is a first order differential equation, then the initial condition involves one piece of information. So the initial condition for that tank is the initial concentration of the salt. When you have a second order differential equation, this is third order, second order differential equation, you need two pieces of information in order to solve for which of the constants are what. And then third order, it's 3, and fourth order is 4. Ooh, you know what I can do? I can even show you. We're going to be doing this. I don't know if we'll do this next week, but I stole this from the physics lab a while back, and you can see I don't think that they want it back anymore because it looks pretty nasty here. But here, let's see if I can not break my neck. Let's see up here. This will be fun. Okay, give me a sec. Yeah, everyone on the video is like, what is going on? So there it is. So there's that. Yeah, this just lives in this room now. But here we go. Oh yeah. So that's actually a second order differential equation. And so in order to come up with the solution to this, we would need two pieces of information. And the two pieces of information that you might have is the initial position of this weight and the initial velocity. So I started out with the weight up here when I hooked it on here. So this is the initial position. Initial velocity is 0. Then I let go of it and it starts moving. So I could do the same thing, but I could start with it here, but I could start by pushing it upward. And that would give it a little different solution. So that had a little upward movement to it. And so you get this nice second order differential equation. Oh, I'll bet you can guess what the solution to this is going to be. Like what kind of functions do you think you're going to get? Oh, it's okay. Don't be scared. What is it? Yeah, sine curve. It's going up and down like a sine curve. Isn't it beautiful? Yeah, we'll solve that one. And probably it'll go about as well as the temperature thing. Because I have we know how much mass this is. It's 500 grams. And we probably can even compute the Hooke's law spring constant for this. We know the acceleration due to gravity, but I'm sure I won't be close. But anyway, so in order to solve this, we're going to need two pieces of information because this is a second order differential equation. Oh, I'm so tempted to go ahead of myself, but I don't want to. So these are all what are called initial and boundary value problems. So when you have an initial value problem, don't write this down. I just wanted to point out that this is exactly what we just had. This is an nth order differential equation. And so you have in pieces of information, in initial conditions. I don't know why I put that in quotes. But so you have the initial position, you have the initial velocity, the initial acceleration, all the way up to whatever this means, the n-1 derivative. So that's an initial value problem. Let's contrast that with what's called a boundary value problem. Boundary value problems, you're given, this is a second order differential equation, so second order. And notice that with a boundary value problem, you have two pieces of information, but those two pieces of information, unlike what I was just saying that we had the initial position and the initial velocity here, the two pieces of information is here's the start, here's the finish. So you would know where you start, where you finish, and basically try to figure out what's happening in between. So that's called a boundary value problem. I guess for obvious reasons that you have initial and terminal position of the object. That's really unnecessary to put here. Okay, so what we're focused on, at least for the time being, is what's going to be called homogeneous equations. Homogeneous equations, we've already had these before. There's no, what are they called? Independent variables. No independent variables. Technically, that's not true because here, I'll just give you an example. dy over dx is equal to y. That is homogeneous. So technically, there is an independent variable. The independent variable is x. But what I mean by no independent variable is that you could write this like this. And the independent variable is invisible to you, so you don't see it. So it's here. It's part of the function. Of course, it has to exist, but you don't have it as part of your equation. There's no x. So that on the right is homogeneous. This on the left is not homogeneous because you can see the independent variable there. So that's what I mean by no independent variable. So homogeneous means you just have dy, dx, and so on. So we're going to be focused on, here's a couple of examples. So some more. Here's homogeneous. Second order homogeneous differential equation. You have 2 times the second derivative of y plus 3 times the first derivative of y minus 5 times y equals 0. And then this is non-homogeneous, where you have the x there, the x cubed, and then the e to the x. So that's the difference between homogeneous and non-homogeneous. Now, where are we heading with this? I need to get this. Here we go. So where we're heading with this is that when you have a homogeneous, actually this is true of non-homogeneous as well, but homogeneous in particular, if you have a homogeneous differential equation, let's just back up to this. In fact, that's too hard for me, so I'm going to back up to something even simpler. Let me write down a simple homogeneous differential equation. So this homogeneous differential equation, is second order. When we try to find solutions to this, what we're going to find is that there are going to be some very special solutions that are going to be called fundamental solutions. So the fundamental solutions to this, fundamental solutions, are going to be y equals sine of x and y equals cosine of x. Those are the fundamental solutions for this differential equation. Now, the reason why I call these fundamental is because every other solution is going to be a linear combination of those two solutions. So those are solutions, but so is this. You can check this will make that differential equation true. So is this. 5 cosine of x minus 3 sine of x. That also is a linear combination of those two functions, and so that will also make this true. So that's why I'm so interested in these fundamental solutions. If I can get my hands on them, then I can solve the differential equation. One last thing about these fundamental solutions is second order means there's 2 of them. Third order, there would be 3 of them. First order, there's only 1 of them. And so here's how this is going to shake out. Let's see, there's so many words here, and I know you guys have told me you don't like words on slides. Let me see if I can get the stuff that's important. How about this? So this sounds fancy, superposition. All this means is that if you have a couple of solutions to a linear differential equation, then to come up with other solutions, you can just add those together. Now, this is a third order differential equation, and so this one is going to have 3 fundamental solutions, 3 linearly independent solutions. So this isn't the full set, but this is at least a start. And if you knew that that was a solution, you can double check this. The third derivative of x squared is 0. The first derivative of x squared is 2x, and of course x squared. So if you plug 0, 2x, and x squared into this, you do get 0. Same thing goes with this one. This one's a little bit harder to check, but you can do the third derivative and the second derivative and the first derivative and plug them all in. So anyway, as long as you know that these are solutions, then anything that looks like this will also be a solution. So that's kind of cool. So one of the tasks that we're going to be, since these are, by the way, it's very important that your fundamental solutions are linearly independent. So what that means is two functions are linearly independent as long as one of them is not a linear combination of the others. So here's the sort of thing that you're going to be asked to do, is to evaluate a bunch of functions and ask the question, are these linearly independent? That is to say, can you take maybe 2 or 3 of these and combine them to make the other one? So that's what it means to be linearly independent, is that it would be impossible. So I'll tell you right now that these are not linearly independent. So as long as you know that, can you guess which functions I can combine to make the missing one, I guess? Like, which ones can you combine to make another one? Take a minute, see if you can, it's like a little puzzle. So I can add or subtract, I can multiply by constants, but you can actually take, I'll tell you 2 of them. You can take 2 of them and combine them to make a third. I'm just going to take this down because we don't need this right now. We'll bring this back next week. Maybe, I don't know if it's next week or not. Yeah, so if Dr. Ho is looking for his 500-gram weight, it's been here for like the past 3 years. I just store it over here. I think he has plenty. I just keep forgetting to return it. Maybe this semester I will. All right, did anyone figure out which ones can be combined? All right, how about this? Take a look at F1 and F2. What if we were to do this? Take F1 or F2 and subtract off F1. What do you get? Oh, yes, there you go. So it's 5x minus 5, which is the same as 5 times F3. So the answer is no, these are not linearly independent. However, it could be extremely difficult to figure out if a bunch of functions are linearly independent because, you know, who's going to be able to come up with all the different ways that you could combine, like this x squared and the x minus 1? So hard. And so there is a shortcut of sorts, and that shortcut is called this equation, this matrix called the Wronskian, named after a mathematician. And so this is a way of figuring out if you have linearly independent functions. So here's the deal. This thing is the Wronskian, that if you have, where's the rule here? I will demonstrate this in just a minute, but here's the rule, is that as long as this is non-zero, then the functions are linearly independent. So let's go back to these functions, and I don't have enough room here because this is kind of a complicated situation. So I'm just going to pull this over to my other app. Give me a sec here. And we'll do the Wronskian. It's a little bit easier to demonstrate than it is to explain just looking at it. Let me get some blank space here. There we go. Okay, so here's my 4 functions, and honestly, well, I don't know, we could, The fourth, yeah, let's do them all, I guess. It's just a little bit of a pain. Okay, so here's how you set this up, this Wronskian, is you start off, well, we start off by trying to move this to a place that, there, up at the top. Okay, so the Wronskian is going to be the determinant. So I'm going to make this big, ugly determinant. 4 by 4 determinant? No. Okay. I'm not going to do it for all four. Let's forget about F4. We know that that's not going to be involved in our, so ignore F4 for a minute. Okay, so we'll just do the 3. It's going to be bad enough with a 3 by 3 matrix. So here, I'll even write it as determinant. So the Wronskian is the determinant of this ugly matrix. So we start off with the functions. So square root of x plus 5, square root of x plus 5x, and x minus 1. And then we're going to take the derivatives of each of these. So we need the derivatives. This is going to be 1/2 x to the negative 1/2. This will be 1/2 x to the negative 1/2 plus 5. And this will be 1. Another set of derivatives. I know, joyous tidings. So this will be negative 1/4 x to the negative 3/2, and this will be the same. And that's 0. So far, so good. So I've got this matrix made up of functions and their derivatives. Now I realize that some of you, or maybe some of the people I'm speaking to on the video, are in linear algebra right now. But if anyone, is anyone in linear right now that wants to volunteer? So have you done determinants? You have not done determinants? Okay, it's going to be all right. What are you doing, vector spaces? Wait, okay, Adric, what are you doing? Multiplying vectors? Okay, vector spaces. You're doing vector spaces. Okay, so yeah, determinant. It's not too hard with a 3 by 3 matrix. Maybe you remember this from the multivariable calculus days, maybe not. So 3 by 3 matrix, the easy, cheesy way of doing it is to augment your matrix with the 2 columns. So I'm just going to copy and paste, but you'd have to actually, so duplicate this, move it over like that. You remember doing this? Sure. And then you do the diagonals. So let's do our diagonals. I know it looks scary, but it's going to be okay. So there's that diagonal, this diagonal. And then the up diagonals are this way, and this way. Okay, I'll even help you out with this. I'll do this diagonal, that's 0. Notice that it's the radical of x plus 5 times this, whatever that is, times 0. So that one was easy. Oh, I'll also do this one for you there. So those are the 2 easy ones. But the rest of these aren't that bad. Let's see, I've run out of room though, so I'm going to move the whole thing downward. Come on. Sorry, it moved up. I want it to go down. There we go. I lost my 0, but I can put it back. Okay, so here's the 0. Very good. So now we just have to multiply through. These aren't as bad as it looks. For example, this down diagonal, the third one, this is going to be x minus 1 times 1 over 2 radical x times negative 1/4 times, I guess, x to the negative 3/2. Okay, that's great. And then this one's kind of ugly. This is going to be 1 times, let's see, radical x plus 5x times 1 times negative 1/4 x to the negative 3/2. Okay, so those are the 2 down diagonals that are non-zero. Let's do the up diagonals that are non-zero. So let's see, this first one is negative 1/4 x to the negative 3/2 times 1/2 x to the negative 1/2 plus 5 times x minus 1. That's probably going to be the worst of the bunch. And then this one, I'm just going to put up there because it's going to run out of room. So this will be negative 1/4 x to the negative 3/2 times 1 times radical x plus 5. Okay, so once you have all of this stuff, you subtract off the up diagonals and add the down diagonals. And I am already regretting my decision to do this one. So I thought that I had one that worked out nicely. Give me a sec. Let me see. I'll look through my PowerPoint. See if there's one that's much nicer. Is it time to go? You're all getting restless? Oh, it is. Well, drat. Okay, so there's homework online. I don't know that it's that hard. Give it a go. Give it a go. We'll figure out what's going on Monday. I guess I've been saved from doing all this. But presumably I would get a lot of stuff would cancel and I'd get 0 if I did that. So we'll find out on Monday maybe. All right, well, thanks for being here. Let me stop the recording in case you want to chat.